Hello, Luke. Yeah. You are the first. The weather is not very welcoming, I guess.
Yeah.
I did look into the work midterm yesterday. You did well. Otherwise, in general, it was not very good performance.
Let me see.
I intended to grade it yesterday, but I couldn't.
I actually struggled a little in the first problem.
Notice.
What?
I noticed in the sense you'd use the whole legendary polynomials.
Yeah, so I did that kind of naturally because I practiced that a lot over the weekend. And when you said that we didn't need to do that, like my work was already done. So I tried to check it with like sort of not using a Legendre polynomial, and it seemed like I was getting a different answer. So
I see.
yeah.
Actually, after seeing your work, I was thinking, okay, if I had not given that comment, it could have probably helped someone else. So, hello, Alia.
Hello, doctor.
Yeah. I promised I'll grade yesterday's work. I haven't yet done it. It should not take too much time. So, just got late. It's only two of you. Yes.
I guess so.
Let's give Weather the excuse and give it a few more minutes. Yeah, just give 2 more minutes. Okay. How was the homework? That was the homework due today, correct?
I think it was okay.
Okay, so that'll be next homework will be the last homework on complex analysis. And this one I typically don't do too much, but since last year I've been trying to do this. This is involving branch cut. It's again often not covered, but I think it's a nice thing to do. So we'll have homework 7 due. Oh, yeah, Moses. Yes. Let's make it due next week, so 27th, Tuesday. And we also have midterm 3. Oh, yeah, so this was one thing. You guys said that you guys don't like the idea that two of the exams come almost one after the other. So I was thinking I should move this exam a little bit further down. Is that what you would prefer? Is the question clear?
When was it gonna be?
This exam is supposed to be November 5th. That's a Thursday. And the following Monday is your ENM exam. So I can move this by, I noticed that there is still time before in November. It's just that it will be too close to the final exam, but the final exam has the buffer of Thanksgiving and there's a lot of things that happen before. So maybe this can be moved by, so in principle, 2 weeks, because if you move just by a week, instead of coming ahead of it, it will come after it. So it doesn't help much. So would you prefer that, or let it stay as it is and not worry about it? Does it really matter? If you guys don't have a specific clear preference, I would just leave it like that.
I don't know that I have a strong preference, but I also see that you could just move the exam one day or like one class period.
Oh, next Friday?
Because it was good, because it's, that one's on Thursday and the EMT exam's on Monday. So if the EMT exam were on Friday, that would be.
That's better.
Okay.
I like that idea. And anything else, Ali or you? Do you have any comments, preference?
No, thank you.
Okay, so I think so. I'll keep this as it is, and as Moses is suggesting, move the ENM exam from Monday to Friday, and that might solve the problem. Okay. Okay. And yeah, again, this is in class, right? Unless I would like it to be strictly in class. Something or the other always happens and puts me in a spot. Okay. We were doing contour integrals. So this is, let's put the title as contour integrals involving branch cuts. This also I wouldn't say addresses it directly, but one could ask the question, oh, yeah, Michael. Yeah. So, are you married now, Michael? How's it work? He doesn't hear us. Michael, can you hear us?
Hi, how's it going?
Yeah. So are you married now?
Not married now. I had to get my marriage license,
Oh, okay.
but we married this week.
Okay. You said 15, right?
What's that?
Did you not say 15? Okay, I was confused.
To the 24th, right?
24th, yes.
Okay. Yeah, I think that was on. Okay. Good. That is Cauchy's theorem. That's an important piece in this whole thing. If we have an analytic function, then the f of z is actually equal to 0, right? If f is analytic. Is analytic inside S. inside the contour C. If that's a closed contour, and inside the contour, if the function is analytic, then it is 0. And we also pointed out that, or I said that it is usually not completely easy to identify the non-analytic points for a function, and that led to some discussion last time, and I did not want to make a strong statement there. So this is sort of gives you more input into, or more examples for what are the kind of non-analytic points you can get. Like earlier, what we have said is, if you have an analytic function and then you divide it by a singular point, then that's a reason for non-analyticity. So for example, so this is called a pole, right? So a pole would be, a contour integral involving a pole would be, you do 2 pi I, and you have an analytic function f of z, but then you divide it by z minus a. So it's very clear that at z equal to a, it blows up. So that's called a pole in the complex plane. And in that case, we found that there is, even though this is having a non-analytic point inside of the contour C, but we can actually sort of circumvent that or exploit that feature to do some integral. So we said this is equal to f of a or 0 if a is inside C and otherwise. And there is another similar concept, and that's where the idea of a branch comes in. So it's called a branch point or a branch line. So what does that mean? So let's so the example is, so let's say we have f is equal to f of z is equal to log of z. And if you notice, if we were to write this in terms of the polar coordinates, so let's say z is equal to r times e raised to I theta. This is log of r times e raised to theta, and this is equal to log of r plus I of theta. But then we immediately see, first thing we can immediately see is that there is a multiplicity. Right? If I were to replace theta with theta plus 2 pi, or for that matter, any multiple of that, this shifts. This will shift a certain amount. So surely there seems to be something off, and let us see the following. Let's have a function f, the same function f if you want, and this is a complex plane, and we want to specify where we are beginning our theta from. Notice you have a choice, right? We can either go from theta going from 0 to 2 pi. That's our choice, actually. Or I can say I go from theta equal to minus pi to pi. Right? Or for that matter, any, I can start from any angle and then come back to that. That's completely my choice. And it seems like this depends on that. And let's see what happens. So if I were to approach a certain point here from this side, so there the value is, so let me mark this out. So here the value is theta tends to 0. And as I approach the x-axis from the top, theta is equal to 0 if I choose my theta going from 0 to 2 pi. And if I were to approach it from the bottom, it seems like it approaches 2 pi. And since this function depends on this theta, so it's clear that the function is not continuous at that point. But we don't know about its derivative, right? If you were to take the derivative, that might go away, right? It is not very obvious that its derivative is discontinuous. In fact, if you were to pick do the Cauchy-Riemann conditions, so Cauchy-Riemann conditions for this would be, so you have your u as log of half of x squared plus y squared. Like if you do this in rectangular coordinates, you have r is square root of x squared plus y squared, and theta is I tan inverse of x y over x, right? And actually, I take back the tan inverse function will have the discontinuity in that, right? But it's a derivative. If you were, if you were to take its derivative, du by dx, this will be equal to x over x squared plus y squared. Du by dy would be y over x squared plus y squared, and du by dv by dy would be the same, and dv by dx would be minus y over x squared plus y squared. So in this case, what we do is that we say this has a branch line on this. This discontinuity is what is called a branch line. This is called a branch line. And the point where it begins from, that's a branch line or branch cut, and this is called a branch point. It seems like it is a discontinuity that is more crucial here. More than the discontinuity, it is actually the multiplicity that is coming in, which is not showing up so well in the way I have described it. But as we do the integral, it will play a bigger role as we look at the Cauchy's theorem around this point. It will play a bigger role. We could. But that's part of your homework, right? Yeah, so in your homework, what I ask you to analyze is that, so that's part of your homework. So I'll just mention it. So you have, this is your complex plane. I ask you to evaluate, assuming that this is the branch. Oh, I should also mention this branch cut is a choice because theta can be chosen from any point. This is a choice. It just has to go from 0 and all the way to infinity. I can choose it as a straight line, or I can choose it somewhere at 60 degrees, and it doesn't even have to be a straight line. It just has to be some line starting from 0 and going all the way to infinity, because I can choose my coordinate system in such a way that's where I begin from. So for each r, I begin from a different 0. So it's not very natural, but in principle, you can do this from any point to any point. And if you do this for more involved functions, we will be doing this for very simple functions. You can have two branch cuts, two discontinuities, one going from here and another going from here, and they can cancel each other. So if you have two branch cuts, if this discontinuity can be cancelled, that's also perfectly fine. So there are a lot of features in there, but I will just do an introductory example, and with that, at least all the essential points would be there, and I will let you guys explore it further. The point I was saying is that in your homework, I asked you to evaluate the integral of this log of z around two contours. So one is going this way, so that's C1. So that means it goes around this branch point, and another one, you go around this. So this. I remember that there is a discontinuity here, so you have to see what actually contributes to this. If it was analytic, then you get a 0, right? So in a way, one way to check analyticity is to do Cauchy-Riemann condition, or once you go the opposite way, you can always say that I'll check my analyticity by going around a circle and see if it gives me 0 or not. If it doesn't give me 0 for every possible point, that's another way of checking analyticity. Okay, so that's just pointing out your homework. So now let's do a specific example where all this comes up, and hopefully that will clarify a lot of things. So the example I want to do is an integral, the contour integral, and let's see, make sure. And again, in your homework, there's a slight variation of the example that you do. I theta is equal to 0 to infinity, and dx square root of x one plus 2x. Is square root of x analytic? Or square root of x, square root of z, I should say, as a complex number, square root of z, is it analytic? It is again like a function of log of z. It seems nice function, x, z, square root of z, but it has a square root which spoils it. See, here there is a multiplicity in theta. So what happens is that if you were to do z is equal to r e raised to I theta, square root of z is square root of r, and then e raised to I theta over 2. So as you approach this point from theta equal to 0, right? So theta equal to 0, it approaches 0. But if you approach it from the bottom, there is a 2 pi here, 2 pi over 2, this is e raised to I pi, which is a different point altogether. So when you approach from here, this gives you e raised to I0, that's equal to 1. When you approach it from the bottom, so this is theta going to 2 pi, e raised to I 2 pi over 2 is equal to minus 1. Right? This is 0 over 2, it's a 1. This is a minus 1, so there is a discontinuity there. Again, this depends on the choice of theta. So on a whole line, there is a, so you would say there is a branch cut all along that line. And you would say this is a branch point. Okay, so square root of z, for that matter, square root of z, any power of z will have this problem. Z raised to 1 over 3 will have a problem, z raised to 1 over 4. Any fraction for that matter will have a problem. Here I do square root of x. In your homework, you have to do this for x raised to 1 over 3. So the whole point remains the same, except that this discontinuity changes. Okay, with that point in mind, so let's proceed in this. Remember that whenever we have a integral of this kind, we have to judicially choose another. If you want to do this using contour integral, we have to choose a contour in the complex plane. Before we reach there, let's see what are the roots of this. Like whenever this goes to 0, first of all, there are poles. Now this has poles here. Whenever this goes to 0, also this has a branch cut. So that's the two mix up here, and that is provided we take this to the complex plane again. At this point, this is just 0 to infinity, x is real. So let's replace cosine theta as, so 2 times cosine theta is e raised to I theta plus e raised to minus I. So that gives me 1 plus 2x cosine theta plus x squared as 1 plus x times e raised to I theta plus x times e raised to minus I theta plus x squared, which is nothing but x plus e raised to I theta times x plus e raised to minus I. Right? That's an observation you make. X squared gives you this term. The cross terms gives you the x times e raised to I theta and x raised to minus I theta. And since these are exponentials with opposite signs, the other term just cancels out and gives you 1. So that's indeed this, which means that this will have a singularity whenever this theta shows up. So let's write that, and that gives us an idea about what the contour integral should be. So let's consider our contour integral to be g of theta. So this is a separate function altogether, which hopefully will have I in it. And this time we go along a contour C. This is dz. And z raised to half. And this is z plus e raised to I theta times z plus e raised to minus I theta. That's a, and again, why did I choose this? This is hoping that some part of the contour that I specify now will have this integral, and rest of the contours can be evaluated. So what is the contour I pick? If I want to use my Cauchy's theorem, I shouldn't be crossing any branch cuts or having any poles in between. If there are poles, then I have to get the residue, I have to circumvent. This has a branch cut all along. If I choose my theta to be from 0 to 2 pi, it has a branch cut all along the positive real axis. Right? That's your branch cut. And it also has poles, right, at exponential of plus I theta, and theta itself is a variable here. In general, theta is a number between 0 to 2 pi, so it could be anywhere. So if theta was, let's say, 60 degrees, that's my exponential of I theta. This is a unit circle here, so this is e raised to plus I theta. But this has a pole at z equal to minus I theta. Where is exponential of minus I theta? So remember that, yeah, I should clarify this, right? This could be, so the poles of this are at z equal to minus e raised to I theta, which is minus itself is -1 is e raised to I pi. Right? So this is e raised to I pi plus theta. So if I have e raised to I theta here, I have to look for e raised to pi plus theta, so I have to add a pi there. So that's down here. So this is my pole. So that's just a point there. That's my pole. The crossed quantity is the pole. And it also has a pole at z equal to minus e raised to minus I theta. E raised to minus I theta is this. So this is e raised to minus I theta. But then I add a pi to that, correct? This is e raised to I pi minus theta. Add a pi to that, I'll be somewhere here. Add or subtract it if you want. So that's, so even though e raised to I theta and e raised to minus theta are here, their poles are on these two points. Okay. So that's your two poles. I can forget these 2 points if you want to. So this is again minus e raised to I theta, and this is minus e raised to minus I theta. So I can forget these two. And now I need a contour, and the suggestion is that the contour could be this. Like you go around this point here, go this way, come all the way down there, and then finish it here. And you're encircling these 2 poles. For that, you use the residue theorem. Again, come down here, go circle, go out, come down here, take a circle, go out. And it all has to be in the counterclockwise sense. This is going this way. Let's give this some labels. So this is C1, C2, C3 is the bigger circle, and eventually come back and C4. Right. So that's your 4 points. So here there are C1 plus C2 plus C3 plus C4. So that's your 100. So the claim is that this integral can be evaluated using this contour integral. Notice along C2 and C4, we are going in opposite directions. And typically, when you go in opposite direction very close by, they cancel each other. Right? That if you go along that's what you do to encircle a pole, right? If you go along an analytic place here like this and then come back here, they will cancel out. So it seems like these two might cancel out, but it doesn't, because there is a discontinuity here, right? The value of the function right above the positive real axis and right below the positive real axis is significantly different. And so they do not cancel each other, and that is how we will, that will help us actually evaluate the integral. Okay, so what is this integral? So let's do this for each of the cases. Right? So let's change the, any questions at this stage? Okay. So we had to do this for 4 different pieces, and there is a residue, right? That is our idea. So let's evaluate this for the contour C1. This is dc, z raised to half, and you have z plus e raised to I theta, and you have z plus e raised to minus. On the contour C1, this has to be taken, I mean, this is supposed to be as small as possible. I can take the limit that epsilon tends to 0. So let me point that out by saying that this is the radius associated with that circle, and that's going to 0. So the substitution I can use in here is z is equal to epsilon e raised to I theta. I keep epsilon constant, but the limit go around from theta equal to 0 to 2 pi. So dz becomes epsilon I theta e raised to I theta, no, I d theta. So that's the same as going from 0 to 2 pi, 0 to 2 pi. Correct? dz is I epsilon e raised to I theta, theta, and that is dz. So this will be square root of epsilon and e raised to I theta over 2. And the small denominator is epsilon e raised to I theta plus e raised to, oh, sorry, I should be careful. I already have a theta in the integral, right? So there is already a theta in here, so I shouldn't be substituting theta, right? So theta is an integral variable, so I should use alpha. Sorry for that. So alpha goes from so the integral is on alpha. And this is still e raised to I theta. This is epsilon e raised to I alpha plus e raised to minus I theta. We are taking the limit epsilon tends to 0. The epsilon is in the denominator because this is always on a unit circle. So these two are always on a unit circle. There is no way this can go to 0 for any angle theta. This will always be on a unit circle, never with the magnitude will go to 0. So that means this will always be small. For log small epsilon, this will always be negligible with respect to that. So this will always be a finite number or a non-zero number in the denominator. In the numerator, you have epsilon tends to 0. So that means this will go to 0. Same thing happens with C3. Let's do that very quickly. So C3 easy. This time we are taking limit r tends to infinity. And that's z raised to half z plus e raised to I theta, z plus e raised to minus I theta. And this time I substitute r times e raised to I alpha. So again, this was limit epsilon tends to 0 here, right? So this time we're taking limit r tends to infinity. You go from I should have also said the limits are actually going from 2 pi to 0 in this case, not 0 to 2 pi, right? Because the contour was running in the opposite sense. So this is actually 2 pi to 0. Just being careful there. But it doesn't matter because anyway it goes to 0. Right? It starts from the contour starts from here and goes away. If you're doing the opposite, then you put in a minus sign. That's also perfectly okay. But it goes to 0, so it doesn't actually matter in this case, but one should. In the contour C3, it actually goes from 0 to 2 pi. And I just had to replace I times r e raised to I alpha, and the square root of r and e raised to I alpha over 2 divided by r e raised to I alpha. And we have to be careful that whether this blows up or not. Again, notice that this is always a unit magnitude. This is on a unit circle. as you take the limit r tends to infinity, this dominates, r dominates. So this is equal to, and the limit r tends to infinity, this is an r raised to 3 by 2 in the numerator, and there is an r square in the denominator. And the integral itself has I e raised to I alpha, e raised to I alpha over 2. And in the denominator, these two are negligible. So that's e raised to I alpha and e raised to I alpha. There are two e raised to alpha. These two can be neglected. These two do not contribute. And there is a d alpha. Whatever this is, this can be integrated out, but the important point is that before even you do that integral, there is a 1 over square root of r, and the limit r tends to infinity, this is 0. Limit r tends to infinity, this goes to 0. So two of the integrals, or two of the contours, the circular part of the contours, that go to 0. And now let's do C2. Z raised to half times Z plus e raised to a, and C plus e raised to minus r I. Now we have to be careful. What do we substitute? So I have C. This is along the x-axis. I want to run it along the x-axis. So it is actually, what is it equal to? So it's a complex number. Let's use the x and y values. So it is running on x, plus there is a small I value, right? So there is a small delta value in there. But how do we capture this correctly so that I can use this in this format? So again, let's go to the polar coordinates. So I want to write this as r. So r is running along the x-axis. And I want to fix, so instead of saying that theta is the one that is variable, I want to say this is I 0 plus a small delta. So let's say this is I delta. So this is equivalent to saying that this is x plus I delta. So this is also x plus I x delta, right? If I take my limit sufficiently small, I can, even after I multiply an x value, I can always reach the value there. So this is going actually a little along the line. So this is, how does this go? So x then goes to r, right? So the way this is going here is that you have this is actually going along an angle. It's not going straight, but that's okay. I can always make my delta take a limit and make this closer and closer. So that's okay, but this is the idea there. But that is just to show what I am doing, but you can always change the contour and get that corrected. The idea is that I'm going to do this as my variable. So r is equal to e raised to I delta. So this is going a little slanted, but it is in the limit delta tends to 0, it will always hug the x-axis. That's idea. In that case, delta is fixed. So this is dr, d is equal to dz, dz is equal to dr times e raised to I delta, right? And the limit delta tends to 0. Delta tends to 0. So that's equal to, along C2, my variable dr runs from 0 to infinity. That's good because that's my actual integral, right? It runs on the x-axis. And the limit delta tends to 0. This is nothing but dr itself, or z. So z is r e raised to I delta. And there was a half. and do the same thing in the denominator. So this is r e raised, oh, alpha again, r e raised to delta plus e raised to I theta, and z is r e raised to I delta plus e raised to I. In the limit delta tends to 0, so this is again limit delta tends to 0. This is nothing but r itself, right? Delta exponential goes away. Even if I were to take delta over 2, that goes away. And this is exactly my e raised to I theta. Sorry, I, which is the integral I want to evaluate. So that's what I would like to calculate. So we just identify that along the contour C2, that's exactly my integral. And remember that C2 is going from 0 all the way to infinity. Let's do C4 now. And that's Z plus e raised to I theta and plus e raised to minus I RT. This time we substitute. Z is equal to r times e raised to slightly below, so it is 2 pi minus delta. It's slightly below the x-axis. And it seems like, oh, it should be behaving the same as this, but it doesn't. So dz would be equal to, in this case, this is equal to dz is dr, and everything else remains the same, right? E raised to I2 pi minus delta, let me write it. Okay. Let's substitute it in here. That's limit delta tends to 0. This time I'm going from infinity to 0, so that's a small change. That's infinity to 0 because the contour is running from the right to the left. This is dr e raised to I2 pi and e raised to minus I delta. Since it is e raised to I2 pi, that's 1, right? Only when there is a change because of the powers I had to worry. So this seems like this will go away. This will also go away. And now comes the change, r times e raised to I2 pi, e raised to minus delta. And when I take the half here, or a square root of this 2 pi switches over to pi. And that changes the sign. E raised to I pi is minus 1. And that will switch the limits. So this is the crucial piece here. Right? This piece and this. This is the difference between going along contour C2 and C4. Like that's coming from the discontinuity. So we are exploiting that discontinuity in a sense. Divided by what is rest of it remains pretty much the same. So this is e raised to I2 pi, e raised to minus I delta plus e raised to I theta. And here it is e raised to I2 pi, e raised to minus I delta plus e raised to, oh, this is minus, right? Minus delta. Copying wrong. In the limit delta tends to 0, many of this goes away. So let me write that here. So this is so now I'm taking the limit delta tends to 0. This is infinity to 0. dr e raised to 2 pi is 1. Here I can do it, but here I should take the 2 pi equal to 1 after I take the square root. This doesn't have any content in there, so that's 1 e raised to minus I delta goes to 1. This is square root of r, and here I get an e raised to I pi. That's crucial. E raised to I pi is minus 1 divided by, this is again r plus e raised to theta. This is r plus e raised to minus I. Which is exactly, I use this, so this is equal to -1. Use this to switch the sign, so this is 0 to pi, sorry, 0 to infinity. That's exactly our integral. Which is again e raised to I theta. So it seems like even though we are going in the opposite sense below the contour, the discontinuity is just sufficient enough to make it the same as your normal integral. This is not going to happen in your case. What will, in your homework, you're doing z raised to 1/3. And that would mean that instead of e raised to I pi here, you will get an e raised to I pi by 3. That would be the big difference in there. So that won't be -1, but either way, this is a factor that comes up. It doesn't change this integral, but it gives you a factor and doesn't cancel out that e raised to I pi. So you get a factor there and you have to keep it. So it's not as clean as here in the sense that it gives you 2 times e raised to I pi. So if you add up all these quantities, so g of theta is equal to 2 times theta. That's what you're sure. Right? But you still have to evaluate, right? We would like to evaluate this. What's the point in equating one integral with another integral? But the point is that this integral can be done. Right? Using Cauchy's theorem, we know what that is equal to. We just have to calculate the residues of it. So that's so once we calculate the residues, then we know exactly what our expression is. So let's go back and let's do the residues. Any questions at this stage?
I have one.
Yes.
So technically, when we take the square root of
Mhm.
the e to the I 2 pi,
Mhm.
shouldn't we, like we can write it as e to the I pi, but we can also, like, there's also a degeneracy there. That's
Yes. Yes.
so
So
I
yes,
guess just like, how does that work?
yeah, good point. Good point, actually. So in principle, yeah, let me keep that. Yeah, so that's a good point. So let's do that here. So in principle, this is actually 2 pi n, right? So this is e raised to I pi over pi n, right? Which will be -1 raised to n, correct? So this is equal to -1 raised to n. So I would say this is -1 raised to n. So the point here was instead of e raised to I 2 pi, I said I'm going to have all possible degeneracies, and this is n equal to 0. If it is 0, it's obvious. So it is 0 plus or minus 1 plus or minus 2, and so on. That's in general, that's what is true. And that was -1 raised to here and here. So this will be -1 and -1, correct? So minus of that. Because I used one of the minuses to do this. So this actually in general is not this. So it is 1. Even better, write this as minus e raised to I pi n times e raised to I theta. Okay. So that will be, that is how usually, if you look into more serious textbooks, that is how you would write this expression. But you can evaluate this for various n's. That's perfectly fine. If you look at integral representations of zeta function, gamma function, and all of these are all standard functions, you will see this expression. And this is exactly the source of that. So they are all evaluated on a branch line, and you will actually get this discontinuity in there, which depends on the choice of your multiplicity. you have a choice there. So there is an arbitrariness in that. So that's good point, very good point. Yeah. So I was being sloppy, I would say. Yeah. Good catch. Yeah. Okay, so let's keep it that way. And the minus sign I did include, and this is e raised to high time. Good. And for your case, what will happen is that this will be pi. This was 2 pi over 2. This will be 2 pi over 3 for your case. And it will turn out that this can be identified as a sine function also. And if I were to pull out e raised to I pi by 2, then this can be identified as a sine function. So sometimes it is written in terms of a sine function also. So that's good. Okay. So with that point, before I proceed, any more questions? Did that help? Did I clarify? Okay. So yeah, thanks for finding that out. Now let's evaluate g of theta using Cauchy's theorem, right? G of theta is also equal to having two residues, right? There are two poles associated with that. So the first pole is I have to multiply by a 2 pi I. Remember 2 pi I times the analytic piece of that. So when I'm evaluating for two poles at minus I theta and minus of e raised to minus I theta. So this is, we have to evaluate this at z over half divided by, the first one is plus, so it is z plus e raised to minus I theta. And I have to evaluate this at the pole. The pole is z raised to minus. Is that clear? So this is the pole. So how you evaluate the pole is, forget that, kill the pole, right? So remember, integral z z minus a is equal to f of a. So first I have to delete this and then evaluate that. So I deleted this piece, the first factor in here. Whatever is remaining, I evaluate this at the pole. Similarly, there is a second pole. So this will be equal to 2 pi I times c half c plus e raised to I theta. That's the second pole. Notice the sign change here. And this time I evaluate this at z equal to minus of minus I theta. This pole contributes the other factor here, and this pole contributes to the other. So you interchange those two values. Okay. So we just have to now substitute things, and we are almost there. So this is equal to 2 pi I z raised to half. So this is good to write this as, yeah, this is just minus 1, right? So that's okay. So, so this is e raised to the square root of minus 1, which is square root of minus 1, and then that is e raised to I theta over 2 divided by minus of e raised to I theta plus e raised to minus I theta. Let's collect these things together. So that's 2 pi I. So that's square root of minus 1 again, which can be going with I, right? So this is e raised to minus I theta over 2. And divided by d is minus e raised to minus I theta plus. Okay, so this is I squared, it's minus 1. I use that to kill the minus 1 in the denominator. It's 2 pi And this is actually a -1. And that's the same as 5. This is e raised to 5, 2. So that's 2 pi. This is if I were to divide by 2I on both numerator and denominator, that's sine of theta over 2 divided by sine of theta. So our integral is, remember, g of theta is 1 minus e raised to I n times I of theta. So I would be, our integral is equal to 2 pi over 1 minus e raised to I pi n and sine theta over 2 divided by okay. When n is equal to 1, we have this to be a factor of 2. When n is equal to 2, that's not very well defined. For every odd n, there is a well-defined structure. Is that clear? There are lots of small things happening, but every step actually is minor. Cauchy's theorem is a broad picture. So in this manner, we will evaluate. Questions? Too many things that happened?
No. Followed it pretty well.
Okay, good. Like this, these ideas play an important role in whenever we define, for example, zeta function. Correct? Zeta function is defined on a complex plane, and it's always along a branch you will evaluate. So I'll touch on that next time. All zeta functions, gamma functions, beta functions, there are all these functions. They are all built up on a one basic contour, and I will do that contour. So it is just a simple 1 over z. So I'll do a simple analytic continuation. So you might have heard the word analytic continuation, like 1 plus 2 plus 3 giving minus 1 over 12. If you ask anyone what's the justification of that, you will say that, oh, this is the zeta function, where zeta function is in a complex plane, it is an analytic continuation, and then you have to come back to get that 1 plus 2 plus 3. So we'll do a very simple version of that, not the zeta function itself, but a very simple. But most of these functions are built on that. You extend from them. So we'll do the very basic, which is basically 1 over x, that function. That's all actually. I finished 10 minutes early. I started 10 minutes late, so so this was a short. That's all. Yeah. Thank you. Yeah. It is a rich feature. If you get interested, explore it. I think the basic pieces are in there. Simple ideas, but very powerful.
Yeah, thank you.
Welcome. Yeah. Oh, Michael, you're back. I thought you had lost Michael for a moment. I thought he left. Probably he's not at home, right? He's using an internet which is not completely reliable. Yeah. Perks of online, right? You can be anywhere and you could be in the car and connecting in principle. And I would upload the homework. It's ready in the sense I just post the old homework. I'm not a fan. I'll do that next half an hour or so. Okay. Do make sure that all these grades get entered. I don't think I usually miss it, but just I have not finalized yet. Oh, except I think your first homework, but I didn't change that yet because most probably I'll be dropping a homework, so that will go away. So I think at this stage I should do that. I should drop the lowest. And I did say, I think before you came, Moses, I think I haven't graded yesterday's work.
Okay.
Any comments on how was the exam? Was it, Aliyah mentioned that it was not as expected because I suggested that I will be giving this as problem, but then I made that as take home and those class problems were not so any.
Yeah.
Was it reasonable? Maybe put it like that.
I thought it was reasonable.
That helps.
Yeah.
Because when I'm making it, I feel that, okay, it should be doable in 1 hour and I make it short. And invariably things go a little, yeah. But most of you did not do good, I should say that. Yeah, it's just probably you guys realized, but I'll be lenient, so I'll be okay.
Yeah.
So especially the second, I expected the second problem to be the easiest, the one with trace of T. And the first one I thought would be the second hardest. And the third one I expected to be the hardest. But
That's what it was for me.
it was for you, yeah. But yeah, everyone struggled with everything, I think, except Luke, I think. But then Luke says that he also struggled. But he got it all right, but he says he struggled. Yeah. So I'll be very lenient. So what I've done is that take home is more percentage. So earlier it is 6 questions, but the percentage is 60% is for take home and 40%, more than 60% is take home, I think, something like that. 40% is in class. And the in-class exam itself, I'll be lenient a lot because otherwise, you guys, most of you guys got most of it wrong in a sense. But you guys all attempted, so we'll see. So it's easy to grade once I'm ready to be lenient. It's hard to grade if I decide I don't want to be lenient. So I just try to give points, that's all. So expect that I will do that soon. Okay.
Got some questions on the homework that's due today.
Sure. Which homework is due today?
6.
Oh, the one for this class, you mean to say?
Yes.
Oh, okay. So it is not yet due, is it?
No, it is due. I just haven't turned it in.
Sure. You want to do that now?
Sure.
Yeah, I think we still have time, and
Okay.
others can leave if you want. Moses has questions, but it's up to you guys. Yeah. So go ahead.
Well, so on the second problem, Seems like it could be,
If you want, or you can just ask me.
that could be solved similarly to kind of the method that we're using in class.
That
So-
seems correct. Square x, yeah, I square, right, plus I, yeah, good.
Right, so that would be those would be the residue kind of solutions, but then you would want to choose a contour interval, and would you want to have the like R would be going to
Yeah, but you don't want to make it full circle, right? Because then you won't be able to catch this minus infinity to plus infinity.
okay.
Idea is,
You want to go across the real line?
yes.
Okay, that was my initial thought. Okay.
So you want to pick, so this is your poles.
Uh-huh.
So you surely want to go along the real line because that's your integral. Right?
Yeah, okay, and that was the other thing, I guess, it became clear in this lecture that I wasn't sure if I should treat.
Because that's my I, right?
Yeah.
And then the question is it this way or that way?
Mhm.
You want to pick that by, you want to choose such a way that this goes to zero.
Right,
This
right,
integral
right, 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 yeah.
So first try this. And by any chance in the limit r comes to infinity, that doesn't go to zero. Then you choose the, so how does that come about is that there is an e raised to I x.
Yes, yes, I remember that.
So remember that there is r cosine theta and then r sine theta, right? I r sine theta.
Yeah.
So I and I make it a negative.
Yeah.
So this is e raised to I minus r sine theta.
Yeah, and then there's a factor of A, which is real.
Exactly.
Yeah.
So you want to make sure that that actually converges.
Yes.
So if it is convergent in the top half, it won't be convergent in the bottom.
Right, right, right.
So pick one. So that's the only crucial thing. And this contributes, right?
Yes.
If you're going the top one, this contributes. Find the residue for this. If you go from
Okay.
bottom, the residue of this.
Okay, that makes sense. I was getting a little confused because I wasn't sure if I needed to choose a contour that encircled both poles.
Because both poles, what will happen is that first of all, you won't get your integral, right?
Mhm.
So, and you want, I mean, there's nothing wrong in choosing that. It's just that it's not useful. Right? If you do this, what will happen is that the upper half plane will go to zero,
Mhm.
bottom half plane will diverge.
Yeah.
Okay, so that's what it is, but that's all, right? And that is, the whole thing is equal to this residue. You don't gain anything out of it. You want to exploit it in the sense that you want to go along this line and say that, oh, that's my integral. Overall, Cauchy's theorem says that that is equal to something and get that.
Gotcha.
Gotcha. So there's nothing wrong with this choice. It's just not useful.
Mhm.
Does that help?
Yep, that does help.
And yeah, take your time, but yeah, let's
Well, I was,
try to submit it
I
today,
was,
but
yeah, I would like to submit it today.
yeah,
I will submit it today. Yeah.
one more.
Well, yeah, so in the very first one, first interval, it seems, well, I guess it's pretty similar, in that we have,
Is it minus?
yes,
And
so we have poles that plus or minus A.
yeah. And then what?
Yeah,
So what is the question?
well, Mike,
Evaluate this.
well, yeah, the question is to evaluate that, yeah.
And what is the C? Oh, C is a unit circle. Oh,
It says to choose oh, yeah, no, that's the,
so probably it's just this. Okay, so you given the contour,
right,
right? You given this, and this is a unit circle.
Yeah.
Right? And there are two poles plus or minus A, right? If A is less than 1,
Right.
If magnitude of A is less than 1,
then it's outside, or that's inside the contour.
then it's inside, right? That's here, right? Then they contribute. Right? So you evaluate the residue at this point, you evaluate the residue at that point.
Right.
But there's a possibility that A is greater than 1, then it is here. Right? Then there is no residue, then it is just 0 immediately.
Yes,
Right? So
that's kind of what I said. I don't think
This is the residue theorem here.
Yes,
Okay.
but-
A is outside the unit circle. Oh, yeah, I is equal to 0, correct.
Yeah.
If it's outside, I is equal to 0. For a less than 1, the poles are inside of the contour. Yeah, good.
so, but do I have to, there's 2 poles. So
There
I
are
have
2
to-
poles. Probably you added the 2.
I didn't add
You
2.
didn't add the 2. So there are 2 of them, right?
Yeah,
So.
that was my
Yeah.
question. Wasn't sure how to.
So how to do that is, so this is the function, right?
Mhm.
Z plus A, Z minus A,
Mhm.
and if you want the 2 pi I also. Correct?
Yeah.
So the
So
residue.
you turn it into a sum, you say that's the function with that pole, and then you sum with that being the function in that pole.
Exactly.
Okay,
That's all. You
Okay.
got that completely right.
okay,
And you evaluate it at the opposite.
okay,
Perfectly.
okay,
Yeah.
okay,
Okay.
cool.
So there is a 2 pi, 2 times A, then there's another piece from the other one.
Right,
That
which I
might
think
come
is a
with it.
minus
Probably.
2A or something, yeah.
Yeah.
Okay,
Good.
thank
Good,
you,
good.
that's helpful. Yeah, I was working on it last night and I actually started in that vein and then I questioned myself and anyway,
Yeah.
I thought it would be better if I asked about it.
Sure. Yeah, maybe I did not go very well in the class for polls and all that.
No, I think it was fine, I just